is chapter 4 on chemical bonding, ACE Chemistry AS level. Chapter 4 is really about shapes and how different atoms are going to bond with other atoms and their strength of bonds based on size and type of bond. First section we're talking about is the different types of bonds. Go by pretty quickly. This is just a review that there's three major bonds. You have ionic, which is the transfer of electrons, and then you have covalent, which can be strong and can be weak. We'll get to that as well. They share electrons, and the metallic bonds are strong, which is a sea of delocalized electrons. So electrons are flowing freely, which makes them useful for conductivity, like copper wiring. So a strong covalent bond is between atoms. Not talking about any intermolecular forces yet. The intermolecular force between covalent bonds are weak. So that is the difference between weak and strong covalent. So you're talking about intermolecular is weak, but intra, between the atoms, are going to be strong. So the reason why they're weak is, one, you have what they call van der Waals forces. So van der Waals forces, there's a temporary movement between positive and negative. So it continuously moves back and forth between positive and negative. So the bonds can't hold on to its positive and negative charge pretty quick or readily. So they disperse, and they're called van der Waals forces. So they're very weak. You have permanent dipole-dipole. That's stronger bonds. You'll see that more in hydrochloric acid or hydrogen chloride or hydrogen iodide, hydrogen sulfide, things that have a permanent positive and negative charge. And then you have hydrogen bonds, which is a type of dipole-dipole, which is stronger bonds. That's only between hydrogen and fluorine, hydrogen and nitrogen, and hydrogen and oxygen. So water, ammonia, and hydrofluoric acid or hydrogen fluoride. Alright, ionic bonds is to transfer electrons. You can see the arrow from sodium, that one electron is going to transfer to chlorine to make it full outer shell. So the outer shell of sodium only has one electron, where chlorine has 7. So the one electron from sodium is going to transfer over to chlorine, and then you have a positive one and a negative one charge. It's a permanent charge. So ionic bonds either lose or gain electrons. The charge depends on the electron gain or loss. If it's going to gain electrons, it becomes negative. If it's going to lose electrons, it is positive. You have, the goal is to be the metal and the non-metal to be noble gas configuration. So the metals are going to lose, non-metals are going to gain. And it forms a positive-negative attraction, which is strong, very strong bond. It's a irregular repeating pattern, so it's a crystalline lattice structure. Alright, to draw a dot cross mod, they use dot cross and ACE. It's very similar to Lewis dot structure. The only difference is they use a cross and a dot. So crosses they use as metals, and the dot in this case is a non-metal. So you can, or the non-metals. So you can see that the metal of the electron from sodium, the cross, is with the chlorine, unpaired electron, to become a noble gas configuration. Use brackets to separate the atoms, and then the charge goes in the upper right hand corner. As you can see here, you just do the outer shell. So sodium is empty, naked, it's lose electron, and chlorine has a full 8 with the X, or the cross, being one from sodium. So if it has multiple electrons transfer, so you need 2 chlorines for calcium chloride, because calcium has 2 electrons to give, so only 1 electron can go to chlorine to give you 8, and then the other one will go to another chlorine atom to give that 8, and you have a positive 2 calcium, a naked electron shell, and then chlorine, both are full with 8, but you need 2 of them. Same thing with magnesium oxide. Now magnesium oxide has 2 electrons from magnesium, and oxygen only, it needs 2 electrons. So you only need 1 of each atom to fulfill its formula. So magnesium becomes +2 and oxygen becomes -2, and they form a ionic bond. Here you can see the calcium chloride again. In this case it's colored, so you can see the dot is, this case, calcium, and they're 1 electron each goes to chlorine, and you have formula calcium chloride. Alright, here's your homework question, one of the homework questions. Make the dot cross of the following ionic compounds and show only the outer shell. Alright, covalent compounds. Covalent is sharing electrons. So the difference is that the bond is actually between the atoms. So there's a sharing of electrons. You can see the dot and the cross are together, forming a covalent bond between chlorine. Now it still follows the noble gas configuration because it has 8 around it each. So it shares those 2 electrons. So those 2 electrons become both part of each atom, chlorine. To make a bond, you show just a little line between the 2 atoms, and that fulfills a pair of electrons. You don't need to include the lone pairs, but you could if you wanted to. So, drawing the molecules, you need a dot and a cross. One atom is going to have a cross, and one is going to have a dot. You draw just the outer shells. And the bond pairs and the lone pairs. And then most molecules are going to follow what we call the octet rule, 8 electrons around it. There's certain circumstances that these don't apply, and we'll cover those as well. So for hydrogen, there's 1 electron each hydrogen, and they will form a bond because it's a pair, and those pairs are shown almost like a Venn diagram, and then you show a bond of the H's. Here, methane. Methane is 4 hydrogens with 1 carbon. Notice carbon has 4 outer electrons. That's because it's in the 4th group. So it needs 4 bonds, and that's why it has 4 hydrogens. So each hydrogen has a dot and a cross, and they're sharing with carbon. You can see there's 8 electrons around carbon, following the octet rule, and then showing the bonds of the structural formula of methane. Water. Oxygen has 6 valence electrons, so it has 2 open spots to pair up. That's why the formula for water is H2O. So you can see oxygen has 2 covalent bonds between H and O. Following the octet rule, again, there's 8 around oxygen. Show the bond between O and H, and then 2 lone pairs on oxygen. Ammonia. Nitrogen has 5 outer electrons, so there's 3 open bonding sites. That's why the formula for ammonia is NH3. So 3 hydrogens form a bond between the nitrogen, and again, nitrogen has 8 electrons around it total, so it has the octet rule. Hydrogen chloride, same idea. Chlorine has 7 valence electrons, so it only has 1 bonding site. That's why the formula for hydrogen chloride is HCl. You can see 8 electrons around chlorine, making the bond HCl. Alright, some anomalies. Boron doesn't follow the octet rule. It is stable with 6 electrons. And then there's certain elements like sulfur, xenon, phosphorus that can break the octet rule and go more than 8. And the reason why it can go more than 8 is because of the d orbitals in the atom. So here's boron. Notice it only has 3 bonding sites, so it is stable with 3 bonds. So for boron trifluoride, you have 3 fluorines with 3 bonds around boron. There's no lone pair. That's important to understand. The lone pair is going to affect the geometry, and we'll talk about geometry soon. Here is sulfur hexafluoride, and when you say sulfur hexafluoride, you gotta say sulfur hexafluoride because that is going to make your voice turn deeper. Like helium turns it higher, sulfur hexafluoride makes it turn deeper. So there's 6 electrons for sulfur. That means there's a possibility of 6 bonding sites. So it's going to break the octet rule, and you have 6 fluorines around it, each one sharing electrons, and then you have 6 fluorine bonding sites, or 6 fluorines bonding to sulfur. All right, check out number 2. Draw a dot cross diagrams for the following molecules: tetrachloromethane, that's 4-chlorine methane, phosphorus trichloride, and bromine. Remember, bromine is diatomic. Multiple bonds. So, oxygen is diatomic. It's going to bond with itself. But if you notice that it has 2 bonding sites. So, that means it's going to form a double bond. So those means 4 electrons are going to share between the 2 atoms, and you get a O2 molecule with a double bond between them. Again, it follows the octet rule. You have 8 electrons around each oxygen. There's 2, 4, 6, 8, and then 8 or 4, 6, 8 around the oxygen on the right. Now carbon dioxide. Carbon has 4 bonding sites, but oxygen only has 2. So again, you're going to form a double bond around oxygen. So you have 2 oxygens to form around carbon because there's an extra bonding site, 2 extra bonding sites on carbon. So again, you're not adding or taking away electrons, you're just sharing them. So 2 electrons from oxygen and 2 from carbon form a double bond. And then on the other side, 2 of each form another double bond. So the formula for the molecule looks like O double bond C double bond O for carbon dioxide. Ethene. Ethene is a double bond carbon. Again, you want to make sure you have 8 electrons around carbon. Ethene has 4 hydrogens, so 4 of them can bond on each carbon, and that leaves you with 4 electrons in the middle, and that's where you form a double bond between the 2 carbons. So you get 2 single bonds on the C and H, a double bond between the C's, and then 2 more single bonds on the C and H. Nitrogen. Nitrogen has 3 bonding sites. So what do you mean? It makes a triple bond. Very good. It does have lone pair on each side because it does have a lone pair by itself. But since it has 3 bonding sites, it can form a triple bond. And that's important to understand that nitrogen makes a triple bond. All right, coordinate bonds. So coordinate bonds are the movement of electrons that only belong to one atom. So for example, ammonium, NH4 plus, is missing an electron. So you have an empty hydrogen electron shell. Now nitrogen has an extra pair. So that is going to form a bond between N and H, not making a covalent bond, but a coordinate bond. So the coordinate bond you can see here is just nitrogen. There's no hydrogen electrons. So that is what a coordinate bond is. You can see here with aluminum chloride, which kind of acts as a covalent compound. It has 2 coordinate bonds here because they both belong to chlorine. So aluminum only has 3 outer electrons. So to be stable, it needs an extra pair, and that comes from chlorine itself. All right, homework question number 3. Draw dot cross models of boron trifluoride and ammonia to form F3BNH3, and then phosphine with a hydrogen ion to form NH4+. All Alright, so bond length and energy. So this is where we get into some topics we'll cover later on more in depth. But you need to understand that as the bond length shrinks, it generally is going to take more energy to break. So for example, the biggest bond length between this table is C and C, single bond carbon. It takes only 350 kilojoules of energy to break. The next biggest is the CO single bond, which takes 360 kilojoules. And then the largest, which is the smallest bond length of 0.116 nanometers, it's a C double bond O of 740. So you can see that bond length and bond energy are directly related, or well, inverse related. The shorter the length, the more energy it has to require to break. So bond energy is the energy needed to break 1 mole of a given bond in a gaseous molecule. It measures the strength of the bond. So the more energy, stronger the bond. So here we have single, double, and triple bonds. And triple bonds are equal to the strongest attraction. They're closest together, and it's going to require more energy to break. And then the easiest one to break, you can see, is hydrogen, which kind of makes sense to its reactivity. Hydrogen is the most reactive of these three, and nitrogen is the least reactive of these three. Alright, let's try this question out. Relationship between the bond length and bond energy. So you can see HCl has the shortest bond length, but also requires the most energy. So they're inverse relationship. Shorter the bond, more energy to break. Why does energy decrease as you get bigger? That's because of the radius. The iodine is a larger atom than bromine, and chlorine is a smaller atom than bromine. So as the size of the atom grows, the bond length is going to grow with it, which means that the bond energy is going to shrink or get lower. Now if you look at the pattern, you should notice that HF should have a smaller length than HCl. So within 0.11 or 0.10, you should have a bond length of HF. Alright, let me know if you have any questions. We can go over that in class, but it's a pretty good introduction to bonding. Make sure you read the chapter and work on those questions.